Thank you, Miguel. And I am very flattered to be here. Thanks very much for the invitation to CEDA. And it's a nice opportunity. There's quite a few friends in the audience. I'm pleased to see you here. I hope that my friends in the audience haven't heard this story too many times before, because, well, I apologize if you have. But so what actually, it was Donatella's, I think, suggestion initially that I address this question about cyber-physical systems and, specifically the question whether this really is a new intellectual challenge. And I'd like to convince you today that it is, and that it's a very interesting intellectual challenge, and that it does have some fundamental twists over many of the things that we've done before. So first, to make sure that we're on the same page, I want to make sure that everyone understands what I mean by cyber-physical systems. So the term itself was actually coined by Helen Gill at the National Science Foundation around 2006, and she helped pull together a community of interest from among academics that she saw as people who would be able to contribute in significant ways to the agenda, and then formed a new program in the National Science Foundation. And of course, many people were very suspicious, rightly so, of any new program, right? Because, is it just a rebranding of things that were actually there to begin with? And what I'd like to today is try to convince you that it is not just a rebranding, that it is actually a very interesting and very fundamental challenge. So first of all, what the field is about the orchestration of networked computational resources with physical systems. So I want to emphasize that, it's not really, you could say, well, this means it's about systems that include computers, so therefore it's embedded systems. But embedded systems, people are really focused on the computing part. And the interesting thing about cyber-physical systems is the conjunction of the computing part and the physical dynamics. Okay, that's where it becomes actually particularly pertinent, and I think where it really is a significant twist on what's been there before. So there's a few examples of the kinds of cyber-physical systems. I love this video from KUKA Robotics, which shows 3 robots that are networked together, that are really orchestrating their actions in a very tightly coordinated way. And I think that's prototypical of what we mean by cyber-physical systems, but the scale of these systems can really get much bigger. So for example, think of a smart grid scenario where you might be covering the state of California in a cyber-physical system, and the physical dynamics of the system is a very important part of the behavior. The other thing that becomes really interesting, though, in the context of these network systems is that when we're talking dynamics, we're also talking about the dynamics of software and the dynamics of networks. And this is something that, software people don't tend to talk about dynamics. They talk about performance. And the two are not the same thing. And so that's, in part, what I'd like to focus on. So the first part that I'd like to zero in on is a little bit of a discussion about what are the appropriate models to use. Now, engineering models have been with us for a long time. Engineers always use models, and we've gotten a lot of success from certain models that I'd like to zero in on. But before I do that, I want to emphasize the distinction between the role that models play in systems versus the reality of systems. Okay. I particularly like a quote from Solomon Ghulam, who wrote a book about mathematical models that I think was very influential, which was really talking about both the strength and the weakness of the use of models. And what he said was, you will never strike oil by drilling through the map. Okay? And that really, I think, is a very important observation. It says that you really have to know very clearly in your head whether you are dealing with a model, i.e. a map, versus a geographic formation, which is physical system. The distinction is very important, and I think that engineers often get so close to their models that they lose sight of that distinction between the model and the physical system being modeled. I want to emphasize that while this is certainly true, you're not going to strike oil by drilling through. This does not in any way diminish the value of a map. okay? This should not be viewed as an indictment of models. The models are still exceedingly useful, but you have to understand where their utility stops, okay? So I'd like to cite one other person, Herman Copetz, who actually taught me something over breakfast at a conference that I happened to run into him. And I've never actually found a very clear articulation of this concept in his papers, although it's there kind of indirectly. But he stated it extremely clearly at this breakfast, and it completely changed my way of thinking about a lot of the things that I was doing. And what he said was that many of the predictive properties that we assert about systems, so these are things like determinism, timeliness, reliability, and safety, that these are actually not properties of systems. Systems don't have properties like determinism, okay? These are properties of the models of the systems, not of the systems themselves, okay? The real strength of the models is that we can make definitive statements about the models, and from those definitive statements, we can infer properties of the system realizations. So when we assert that a system is deterministic, that's actually not a legitimate statement about any physical system. No physical system is deterministic. How's it going to behave while it's being crushed? Okay? How's it going to behave when it's at the bottom of the sea? You know, you don't know. It's not deterministic, but the model. Now, we have gotten enormous power from deterministic models. And I'm going to apologize right up front to those of you in the room who work on asynchronous logic and on probabilistic circuits that may or may not give you the right result. I sympathize with your challenge because you've got an enormous uphill battle to fight, which is to deliver the value that people in the circuits world have gotten out of deterministic models of circuits, okay? So synchronous digital logic, that concept is a model, okay? It's a model that is talking about rather messy behaviors of transistors and so on, but it's an extremely powerful model. And I would say that a huge part of the information technology revolution actually depends on this model. The fact that you can, produce a microprocessor that will correctly execute a particular chunk of code perfectly, essentially perfectly reliably, over and over again, 1 billion times a second, and work correctly for years, okay? The predictability and the determinism of that model is a very, very powerful thing, and it's not something that we should give up lightly. You could say, well, no physical system is deterministic, so we should give up determinism. And you're throwing out the baby with the bathwater, okay? It's true, no physical system is deterministic, but you don't give up models that have this power easily and lightly. Another example of a deterministic model that has had a huge impact in the development of our technology is single-threaded imperative programs, okay? These are models. These are models of a process, of an algorithm, okay? And they get executed, in fact, on the same hardware that is ultimately built on this synchronous digital logic, but it's a different model, okay? It's quite a different model. Anyone who has written multi-threaded programs knows the price that you pay when you lose this determinism, right? It hurts, believe me, it really hurts, okay? It costs a lot to lose determinism in this case. And an awful lot of what we depend on in software is, in fact, the determinism that arises from being able to be assured of correct execution of a deterministic single-threaded imperative program. What about the physical world? Well, in the physical world, we have also, for hundreds of years now, derived enormous benefit from deterministic models. You've got some physical system this is a generator, okay, that will produce electric power. We have models that have been developed and refined over hundreds of years, differential equation models that are fundamentally deterministic. I'm not saying that we don't have also non-deterministic models and even probabilistic models. Those are okay. What I'm emphasizing here is the power that we've gotten from the deterministic models, that they've given us an ability to design control systems, for example. I mean, you could say, all right, the feedback control system that keeps a helicopter in the air, how is that designed? It's designed using deterministic differential equation models. Is the helicopter deterministic? No, of course not. But we wouldn't be able to design that control system if we didn't have that powerful engineering abstraction, okay? So we don't want to lose sight of the power of the engineering abstraction. Okay, so we've got powerful models for software. We've got powerful models for hardware. We've got powerful models for physical systems. What happens when we put them together? Today, they become non-deterministic across the board immediately. Non-deterministic, okay? We don't have deterministic models for the composition of that single-threaded imperative program and that generator. They're not there, okay? So here's a simple schematic of a cyber-physical system. A cyber-physical system has a physical plant. It's got one or more computational platforms, microprocessors. It's got some network fabric, okay? And we have models for the pieces, okay? We give the model of the computational platform as an imperative program. We give a model of a physical plant. However, when we put them together, these models actually don't work together in a deterministic way. Why? Well, let's look at the software. So here's a very simple, very short sequence of actual C code that is meant to do something for 2 seconds and then stop doing it, okay? And so it seems to be actually expressing behavior that is going to affect the physical world in some predictable way because, of course, we're trying to take some action for a particular period of time in the physical world and then start doing something else, okay? But here's my question. This program is a model, okay? Does it specify timing behavior? The answer is actually no. It doesn't say anything about timing behavior, right? It in fact says, okay, well, you've got a C procedure. Within the six of the procedure of C, you've got a procedure that must be called. Interestingly enough, it looks like from looking at this program, this procedure is never called. So actually, unless you tell the compiler not to do it, it could optimize away this procedure because it's never called. It's going to be called by an interrupt service routine. How does that happen? Well, that happens because we invoke another C procedure that writes a binary pattern into a memory mapped register, which happens to tell the hardware that it should invoke a interrupt service routine, okay? And it writes into other memory mapped registers to control a timer. So where is the timing behavior in this model? Well, the timing behavior is actually not in the model. It's just simply not there. Behavior shows up when you combine this model with a physical system, with the physical realization of the system, a particular board. This same program will behave differently even if it's the same microprocessor, but a different board, okay? The program will behave differently. Even the same board, right? The program may behave differently in different environmental conditions, right? Nothing about the model gives the timing of the interaction between that program and the physical world. In effect, the designer of this system is working without a model. The designer of this system is stuck working with the physical realization only and not really leverage models. So what are the consequences of this? Well, one consequence immediately is that if timing affects system behavior, then designs end up being brittle. What brittleness means is that small changes in the environmental operating conditions or something like that can have big consequences, right? We don't have the robustness that we have with deterministic models. They're just not there. As a consequence, I heard this story first from Boeing, which is probably the most extreme case, but I've checked with all companies that make cyberphysical systems have this problem. If they're going to have a production run of some product, they stockpile the electronics for these things, hopefully for the entire production run. In the case of Boeing, when they introduce a new aircraft, they expect to make it for about 50 years, okay? So they will probably still be making Boeing 777s in the year 2030, and they will be using microprocessors that were made in the early 1990s. They're storing these microprocessors in nitrogen because they're afraid that the diffusion processes, the natural diffusion processes in the silicon will degrade the microprocessor so they won't work in 2030. Wait a minute, a microprocessor, synchronous digital logic, running single-threaded imperative programs. They're not allowed to use threads for safety-critical code. The microprocessor, any microprocessor, will correctly execute that code. It'll, in fact, any microprocessor will do what it says. Unfortunately, the model doesn't say what needs to be done. It doesn't say how this program should interact with the physical world. It's just not there in the model. So it's not enough to correctly execute that model. You're stuck with the physical implementation of the system, which is why you have to stockpile the parts. Okay? You can't take advantage of improvements in the hardware. Okay? If you do, if you want to, reduce your costs, reduce your power consumption, whatever, everyone experiences this. You end up having to completely retest systems. Very expensive proposition. You end up over-provisioning designs, increasing the cost and the weight and the energy usage. Okay? So why is this? Well, the model is not up to snuff, right? This model of single-threaded imperative programs is useful for describing algorithms. It's not useful for describing cyber-physical dynamics, okay? It doesn't do that. It was never intended to do that. It was intended to describe algorithms. And in fact, where you can see this is that the notion of a correct execution of a program in any widely used programming language today has nothing to do with how long it takes to do anything. That has no bearing on correctness, okay? Programmers have to step outside of the programming abstractions in order to specify timing behavior. In effect, programmers have no map, okay? They're just tinkering with physical systems, going without a map, okay? It's kind of like if you're going to drill for oil, don't use a map. Just start drilling wherever you happen to be. We know that's not going to be a very cost-effective solution, but this is what we do today when we design cyber-physical systems. Now, computer science hasn't completely ignored timing, of course. In fact, I credit my colleague David Patterson and John Hennessy with having, kind of revolutionized computer architecture by really emphasizing a sort of quantitative, timing-based qualification for computer architecture ideas, right? But today, timing for computers is a performance metric, not a correctness criterion. Correctness is about the relationship between the physical system and the model, okay? Performance is something else altogether. They're not the same concept. They're not the same thing. So let me emphasize what I mean by correctness. So here's a short segment of C code. And in every correct execution of this code, line 8 will not execute, okay? That's a fact. If line 8 executes, there is something wrong in the physical realization. Now, could line 8 execute in a physical realization? Yes, of course. You could get an alpha particle that changes the state of your program counter, and the program starts executing line 8. That's always true of a physical realization. The physical realization isn't deterministic, but in the model, line 8 does not execute. Right? If people who work in formal verification depend on the strength of an assertion like that. It's a mathematical assertion, and it's an assertion about the model, okay? That's what we mean by a correctness criterion. In effect, when you have such correctness criteria, you can develop absolute confidence in systems. Absolute confidence. Wow, that's a really strong statement. What do I mean by that? Well, what I mean by that, of course, is not that it will never fail. But what I mean by that is that only a hardware failure is an excuse. That's your only excuse for not doing this correctly, is a hardware failure. Okay, so then you try to make your hardware reliable, and you can get very high confidence in a physical realization. But in the model, you can have absolute confidence. Okay? Very powerful concept. But unfortunately, there are no such assertions we can make in software. We see this, any timing analysis that you do on programs today requires you to have a description of the silicon that's going to execute the program, okay? You have to know everything about the silicon. It's not enough to know the instruction set architecture. None of the abstractions of the system are actually useful. You need to know what the silicon is, okay? But the hardware that we build the computers out of actually is perfectly capable of very repeatable, controllable, predictable timing, right? Synchronous digital logic. It's just that the software abstractions discard that property of the abstraction. So I come to the first challenge in cyber-physical systems, which I consider to be a big challenge and a challenge to this community and to others, which is that we need to change programming models so that a correct execution of the program always delivers the same temporal behavior up to some precision. We're going to have to talk about precision. In fact, I'll get to that later. What do I mean by correct temporal behavior? Okay? But the idea is to introduce a correctness criterion. We need, in effect, determinate cyber-physical system models. That's the essence. We don't have them today. Now, of course, this is going to require changing some things people hold dear to their heart. And unfortunately, you know, engineers tend to be very conservative in the tools that they use. And there's a powerful inertia created by existing languages, tools, and methodologies. So we need to have open minds. We're going to need to do some experimentation, which is why I think, you know, cyber-physical systems is a wonderful thing to be doing research in, because it needs fundamentally new techniques, and it's the people with open minds who are going to succeed in this research. But wait, it's not that simple, as if that were simple. I mentioned timing, right? If we want a correctness criterion that says that a piece of code will interact with the physical world with some repeatable timing. Well, what do I mean by that, right? What is time, okay? That's actually something that we could get very philosophical about, right? But the issue is that we're going to need models again. And these models are not it's not necessarily obvious what the right models are for talking time. So if your focus is on the physical plant, you might use a model like this. This is a very simple physical plant. Of course, real physical plants are more interesting. But it's got this little magic variable t, okay? And people who are in engineering disciplines that are primarily focused on physical devices use that variable t quite liberally, as if there was, you know, some universally available fabric of time that you can just ask, what time is it, right? So this is what I call the idealized Newtonian notion of time. In a cyber-physical system, you've also got these computational platforms. Do they have access to T? Well, no, they don't, actually. They can make measurements, okay? But those measurements are going to be imperfect. And there's going to be discrepancies in their measurements. Any two platforms on a network are going to disagree on what the time of day is. You can, you know, no matter how much effort you put into time synchronization and clock distribution and so on, there's going to be discrepancies. So you need a model of time that is robust to those discrepancies. So there are naive answers to these. The Newtonian idealized physical notion of time. In the software world, it's just a double, okay? Which is a really poor choice for a model of time. The hardware designers know this, right? But software designers don't seem to know this yet. They'll discover it, right? It has the property that the precision with which you measure time depends on the magnitude of time. That's probably not a good idea. It's very hard to have a clean notion of simultaneity when your semantic representation of time is a double. Very difficult to do. So there's a lot of interesting questions here. Time synchronization, what role should that play? How about precision of time? How about representation of time? People have talked about superdense times, hyperdense times, multiform time, where you have timelines proceeding at different rates in different parts of the system. Very interesting problem, lots of good work to be done, some good work to be drawn upon as well, okay? Challenge number 3, can we develop a model of time that is consistent with the realities of time measurement and time synchronization, and also with the engineering models that are used in physical systems, okay? So in essence, we need a semantics of time. All right, already, hopefully, I've convinced you that this is not, we're not talking about a lightweight problem area anymore, okay? There's deep problems here, but there's more, okay? The next set of problems that I'd like to address are ones that are really more cultural problems. They're problems that humans have getting their heads around complexity in systems. So I'm going to talk about the problem of model engineering. Okay, so here's our canonical cyber-physical system, having this physical plant, a computational platform, and a network fabric. So the problem here is that any interesting cyber-physical system is a multi-vendor system, multi-physics, with a variety of different models coming into play in different parts of the design. We have the blind men and the elephant problem, which is that any individual who looks at this system sees it through their own blinders and sees only the part of the system that they are immediately familiar with, right? So let me give a concrete example. Let's talk about the electric power system for an aircraft. Electric power systems for aircraft have been in the news quite a bit because of the grounding of the Dreamliner due to the problems with the batteries, right? It turns out these systems are very interesting and rather complex cyber-physical systems. This happens to be a diagram right here from a Honeywell patent showing some innovations. And the key thing to notice is that there's 6 generators up here. Some of them are DC generators, some of them are AC generators. There's a bunch of buses. There's a bunch of contactors, which are switches that you can throw to connect buses. And there's a bunch of loads, which are simply the things that you're going to have to deliver electric power to. And there's lots of complicated constraints, right? And some of them are very simple constraints. Don't connect an AC bus to a DC bus. Don't connect 2 DC generators together on the same bus. Don't leave any load unpowered for more than a certain amount of time. Things like that, okay? These are all constraints on the design. But when you look at a system like this, let's take a much smaller version of it than what's in the patent. So this is just as a single generator, a single contactor, a single bus, and a single load, okay? So there's kind of the plant. And it has a PID controller that's controlling the generator to keep the voltage and the frequency regulated. It's got some protection logic that's making sure to protect the load, for example, against overvoltage conditions. It's got a supervisory controller that is regulating the contactor to determine whether the contactor should be open or closed. And it's got commands coming from the pilot to turn on or off the load, okay? Very simple subsystem, and it's already an elephant, okay, that a bunch of blind men are looking at, right? If you happen to be an expert in electromechanical systems, you might be focused on the generator. If you're a mechanical engineer, you focus on the fact that the contactor has physical dynamics and it could bounce, for example. You have to worry about the bouncing on contactors, okay? If you're an electrical engineer, you might be focused on how the bus is handling the distribution of the electric power. If you're a control systems engineer, you're focused on the control system design. How do you do a PID controller to control this generator? If you're a software person, you're probably focused on this supervisory controller. What is the logic of that? How do you prove correctness of the supervisory control? If you're a networking guy, you're worried about how, notice these things are actually getting implemented on different microprocessors separated by a network, so it's a communication problem. If you're a human-computer interface problem, this is the pilot control problem. You're worried about fusion, for example. If your overvoltage protection kicks in, will the pilot know it? There's a bunch of engineers here with different backgrounds looking at this problem in radically different ways. And this is a very small cyber-physical system problem, okay? So, number 4, how can we define interfaces between components that bridge engineering disciplines and clarify requirements and expectations? In essence, what I'm calling for is we need a discipline of model engineering, okay? I call this model engineering sort of analogously to software engineering, but software engineering becomes a subset in a sense because you have to do software engineering as part of this. But really what you want to be doing is engineering complex models with well-defined interfaces between heterogeneous components. And one nice thing about this phrase, model engineering, is that if you master it, you can be a model engineer, which I sort of like the idea of being. So, all right, I've raised some interesting challenges. How do we approach these challenges? Well, I'd like to spend my remaining time just telling you a few little vignettes about things that we're doing at Berkeley to try to address these problems, okay? Because I hopefully have convinced you that the problems are interesting and rich enough to warrant some effort, okay? What I'd like to next convince you of is that there's some very interesting things we can do and there's a lot more to be done. So here's a list of some of the particular projects that we have going on right now, and each one of these would be another hour talk at least to go into any depth. So what I'd like to do is just kind of a once-over that tries to tell you where I see the opportunities are in addressing these problems. So let me start with the PRET machines project. So PRET is an acronym that I really like because it has at least 5 different meanings, right? It stands for precision timed processors. It stands for predictable, repeatable timing. It stands for performance with repeatable timing. That's an important one because you can get repeatable timing from microprocessors if you're willing to give up performance. It's very easy, okay? In fact, all you have to do is go find, maybe Boeing has some in liquid nitrogen. Go find some old Intel 8080s, and they will be PRET machines, in fact. They're perfectly controllable timing, okay? PRET is also the French word for ready and the Dutch word for fun, which I like all of those meanings. So what is the goal of this project? The goal of this project is to rethink the notion of an instruction set architecture. So the notion of an instruction set architecture is a very powerful abstraction that computer architects have gotten a lot of leverage from, right? It's a huge value in that abstraction. But by choice, instruction set architectures have no temporal semantics. That's a choice that was made when the concept of instruction set architectures was originally developed at IBM in the early 1960s when they were developing the IBM 360 family of mainframes. And the reason, of course, is that you don't need temporal semantics to run payrolls. And that's what IBM 360 machines did. They were room-sized machines that ran payrolls, primarily. And who cares about the timing? I mean, yeah, the checks need to be printed before tomorrow, but you've got a lot of flexibility, right? So the instruction set architectures did not need that. They didn't need to expose that property of the hardware, that timing is controllable. It wasn't necessary, okay? And that hasn't been rethought since. The instruction set architectures today still do not in any way expose timing. And as a consequence, there's a layer of abstraction that all software systems are using that is hiding a property of the underlying hardware, which is that timing is, in fact, controllable and can be made precise. It hides that. And if you want to regain it at higher levels of abstraction, you end up giving up many orders of magnitude in precision in order to regain it. You do it using, for example, external timers and timer interrupts and things like that. Okay? So the PRET machine project is to say, well, okay, we believe that you can, in fact, get precise timing into an instruction set architecture without sacrificing performance. And if you go to this website, you'll find some papers that show that not only do you not sacrifice performance, but in certain cases, you actually improve performance. So you can get performance gains along with getting control over timing, which was a little unexpected. We always thought that we would have to give up something in performance, but it turns out, actually, that's not the case. So I encourage you to take a look at that project. So let me talk about some of the other approaches. So model-based design. This is one that is addressing the model engineering problem. And Miguel mentioned discrete event model at the top level, the continuous time dynamic. The PID controller, of course, is really just a sample data signal processing system. So we could use a data flow model for that. In this case, this model is using a synchronous data flow director. It's a rather trivial model. It's only got 3 actors, okay? But nonetheless, it is using a different modeling paradigm that nonetheless combines in a deterministic way with these others. The supervisory controller is itself a state machine, which is a completely different kind of model from the ODEs and from the discrete event model and from the data flow model, completely different, okay? It's just specifying the state transitions that occur and so on. Okay, so this is our attempt to address this blind men and the elephant problem, which is to have well-defined interfaces between these distinct modeling regimes, where each of these modeling regimes is perhaps pertinent to maybe only a subset of the engineers who are working on a project, right? So the people who work on on the ordinary differential equation models are not going to be the same people who are working on the supervisory controller necessarily. They're going to be working with different models. They're going to be working with different modeling paradigms. The key is to get these modeling paradigms to work together. Now, there's always then the question of modeling tools. And I want to emphasize that it's a different problem to combine modeling tools than it is to combine modeling paradigms. Okay? Combining modeling tools is a much harder problem because there's a lot of accidental complexity in it. There's just the problem of, oh, the tools are written in different languages, or the APIs aren't published, or the APIs aren't documented, and they change with versions of the tools, or the tools don't run on the same platform, or huge numbers of just accidental complexities. Tool integration is a nightmare of accidental complexities, okay? It's not, from my perspective, tool integration is not an interesting problem. Integration of paradigms is the interesting problem. And if you solve that, the tool integration will follow because people will figure out how to define the interfaces between the tools. I'm personally particularly enthusiastic about an effort that is still, a little bit raw and has some rough edges, but the FMI effort, which is being led by the Modelica community, to define an interoperability standard between at least a certain class of tools that can represent these kinds of systems. And we've got some existence proofs that it's possible, for example, to take a model in Modelica, which is a very different style of model than the differential equations model. So this is a generator and load specified in open Modelica. And the interesting thing, just to emphasize how different this is from a Simulink style model, the ports on this generator are not inputs and outputs, okay? They're electrical connections. So just like you would have, a connector on a generator, is it an input or an output? Well, actually, the voltage produced by a generator doesn't just depend on what the generator does. It also depends on the load. So if you're measuring the voltage across 2 pins on a generator, is that an output? No, not really. It's a kind of a negotiation, right? So this is what people call acausal modeling. And it's something that Modelica does really quite well. You can embed that, however, using this FMI standard into other very different kinds of modeling paradigms, such as this discrete event modeling paradigm. So this is, I think, a promising direction and work that I'm quite enthusiastic about. Now, let me also talk about another issue that so far I've shown you this generator load as a very heterogeneous model, right? We've got software, we've got physical dynamics, we've got data flow, we've got control system design. What about the hardware, okay, that we're going to implement this thing on? Suppose we're trying to decide, well, what kind of buses do we need? How many processors do we need? What's the interconnection mechanism going to be? What's the scheduling protocol going to be, right? One way to do it would be to take this same model and start to elaborate it. Okay, the communications between these things are, in fact, discrete event communications. Therefore, I know how to construct discrete event models of networks. I could insert a model of a network here and have all my communications go through that network component. But this is going to create a problem for the engineers working on this because the control systems guy really doesn't care about the details of the network, right? He does care, he or she does care about the latencies that the network introduces, right? But not really about the routing protocols and how those latencies are achieved. And the model is going to get muddied with details about the network if you just take this model and elaborate it. By the way, when people build models like these, okay, one of the things that I've been battling against is that they very quickly become proud of the complexity of their models. And I keep telling them, you should be embarrassed by the complexity of your models. Useful models are simple models, right? As soon as they become complex, they become less useful. So the question is, how can you keep your models simple and still have them reflect the behaviors that you're interested in studying? So we've been working on what we call aspect-oriented modeling, which is inspired, the term comes from aspect-oriented programming, which Gregor Kiksalis was kind of a pioneer in this area with the creation of AspectJ. And the idea in aspect-oriented programming is that suppose you have a program and you're interested in, say, all of the calls to certain procedures that maybe access the TCP/IP stack. You might be doing this for security analysis, for example. You want to do security analysis on a program. You want to see where in the program it accesses the network and how it accesses the network. So one way to do it would be get the source code for the program, and every time there's a call to something in the TCP/IP stack, insert in the source code a call to something else, right? That's going to monitor those actions, for example. Well, that would be the non-aspect-oriented way, and that's the approach that is the muddying of models. It's combining models, describing different things in a way that then becomes very hard to disentangle. Okay, so the aspect-oriented idea is that what you do instead is you leave the original program unchanged, and you create a new program that is describing an aspect. Okay, and as part of the declaration of that program, it says, okay, whenever this thing happens in the original program, I want this to happen in my new program, okay? But you keep the two programs separate. So you can maintain them separately. The engineers who are working on them can work on them independently. And then under the hood, you provide tools that weave these programs together so that you can analyze the behavior under these aspects, okay? So this idea of weaving together behaviors is the key. So here, what we've done is added these two little components in here, which are actually two different simple models of two different processor architectures on which we might run this supervisory controller and this PID controller, okay? So in particular, the two-processor model is just a very simple model of two processors. This is with a dumb scheduling algorithm, but you could elaborate this with a more interesting scheduling algorithm. But the scheduling algorithm is simply first come, first serve. A request comes in to execute a task here, and on this processor, you simply execute it on that processor, which is modeled by a server. So you queue up tasks that haven't been processed yet. When the processor becomes free, you execute the task for some specified amount of time, and then you issue a response, right? And we have a second processor that will also similarly process tasks first in, first out on a queue, okay? So we can weave that model with this original model just by setting a single parameter that says, okay, I'd like to use the two-processor model, and then I can run a simulation of this and observe the dynamic behavior of that woven model, okay? But the two models are separately maintained. I can simply substitute in a single processor model, which simply takes the requests that are coming in on these same two request lines and combines them into a single queue and server, okay? And I'm going to get different behavior from the system as a consequence of that choice of the other model, right? The key thing here is to separate these models, right? So this particular effort we call Metronomy because probably many of you would recognize this approach as having been pioneered by my colleague Alberto Sangiovanni Vincentelli, who in the Metropolis project really introduced this idea of weaving together platform models with models of the functionality, okay? So Metronomy is our combination of Metropolis and Ptolemy that is pulling together these ideas within a framework that provides for this separate but conjoined modeling techniques. Okay, so the four big challenges that I've identified are coming up with determinate cyber-physical systems models. And I'm certainly very interested in arguing with people about the value of determinism, but I'm afraid that history is on my side on that. We have gotten tremendous power from deterministic models. And so I think the fact that we have no such models for cyber-physical systems, in my view, is just an enormous gap. We need to have open minds about languages and tools. Interestingly, in my experience, I interact a lot with software people and with hardware people, and I find that hardware people are way more open-minded than software people. I don't know why this is, but it is. We need a semantics of time. Time is not a simple concept in practice in systems, and we need a semantics so that we can talk about models of time that have rigorous properties. And we need a discipline of model engineering to pull these things together. So Thank you very much. I'm happy to open this up for questions.